So today I'm going to be talking a bit about how we form stars. So as you can guess from the title, we form them from gas, mainly from hydrogen. So I think it's appropriate to start with a brief history of hydrogen, which, as the quote says, is a light, odorless gas, which, given enough time, turns into people. So as most of you are already aware, after the Big Bang, most of the mass was either in dark energy, dark matter, or hydrogen. So most of that dark matter and hydrogen coalesced into what we call galaxies. And within these galaxies, the gas itself later formed these dense structures, which we call stars, which ignited fusion. And through these fusion processes, heavier elements like carbon and oxygen, what we are made of, was synthesized. So, as I mentioned today, I will be talking about this part of the process, how we go from gas to stars. So, if we are interested in this process, we can actually observe it on the sky. And I think this is going to look a bit familiar today. So, if we look up in the sky with a space telescope like Hubble and we look for a region where stars are forming, there are a bunch of them around us. So, what we find is that this mostly happens in, as I said, very familiar. It mostly happens in gas clouds. So like the pillars of creation here, where it's an active star-forming region where newborn stars are actually competing with the older ones for material. So, okay, this is how it looks in the optical. And as Rebecca told us, if we look at it in an infrared, if you look at gas clouds in infrared, we can actually infer a lot more information. Although maybe with this contrast not that much, but still. So the idea is that stars mostly form in these clouds of molecular hydrogen, which you can see a picture of one of the Orion clouds here. And if you zoom in a bit, you will find, and I hope you can see that in this infrared picture, you can see that the gas actually has this filamentary structure, and along these filaments you find these like bright spots here. These are like dense little clumps that people usually call cores. So these cores, these clumps of gas, collapse to form stars. So of course, since this is an astronomy or physics talk, let's talk about how that really happens. So here is a simple picture of how stars form out of gas. Essentially, you have two forces. You have gravity, which tries to squeeze the gas to shrink the cloud. And we have pressure, which tries to resist it. And essentially what happens is that when the gravitational force is stronger than pressure, then it overpowers it and makes the gas collapse. So if you look at the math part, don't have to, I'm just going to tell you what it says. If you look at the mass part, you will realize that actually to collapse, you will probably need low temperatures because that lowers the pressure, or high density because that increases the gravitational force. So from that, you can guess that gas clouds collapse if they are cold and dense. So just to give you an idea what me and other astrophysicists in this context mean by cold and dense. So by cold, we mean 10 Kelvin. So just to imagine how cold that is, if the air around you was 10 Kelvin, it would be solid. And the density is 1,000 molecules per cubic centimeter. Well, that's hard to put in context, but that density compared to the density of the air in the room is similar as comparing the size of Texas to a fingernail. So to our standards, it's not dense at all, but compared to space, empty space, this is actually very dense. Okay, so this is a simple picture, and I think we all agree. It's very easy to understand. Gas collapses, it's simple. What's the problem? So as with all problems, there is always a simple, neat solution. That is, of course, wrong. And that's true in this case, too. Star formation is not just gas collapsing under gravity, there is actually a whole lot of other complications to make things a lot messier. All of these are the subject of current research, and I'm just going to try to give you a glimpse of what each of them does. But if you are interested, I can tell you that we don't really know, actually. But, we have some ideas. So first, let's start with turbulence, one of the oldest unsolved problems of physics. So if you have ever drank coffee or tea, or you have all been near water. You have all seen turbulence. We all know what it is. It's essentially this messy, chaotic motion of fluids. And of course, the gas that I just told you was going to collapse under gravity is, of course, going to become turbulent. And what that means is that this whole picture of this nice ball of gas shrinking, that's not at all how it's going to, behave. It's going to be a lot messier. Of course, there are other issues here, like magnetic fields. Of course, some of you might immediately say, wait a second, David, that doesn't make any sense. This gas is neutral, and magnetic fields only interact with charged particles. So why do we care? So the problem is that this gas is not completely neutral. It still has charged particles in it. And these charged particles do couple to the magnetic field. So just to help you imagine what happens, if there is a magnetic field, like this blue line, a particle can essentially only move along it in this nice spiral trajectory. So essentially what happens is that some part of the gas is coupled to the magnetic field. And of course, these particles can interact with the other particles of the gas. Essentially, this means that the magnetic field is coupled to the gas itself. The reason it's important is because magnetic fields don't like to be squeezed. And so when the gas collapses, these magnetic fields will help it resist collapse. So just to show you what this means, this is a simulation of collapsing gas. So the lighter the color, the denser the gas is. And it's pretty hard to make out at this point, but these little black things are actually arrows showing the strength and direction of the magnetic field. The larger the arrow, the stronger it is. So what happens essentially is that initially you had these tiny arrows. The magnetic field was essentially inconsequential. But as the gas collapses, the magnetic field increases drastically and helps it resist collapse. So let's say we are interested in, let's say we try to zoom in to what happens in this little collapse region, how the magnetic field really looks there. And we have these kind of structures there. So if you can tell me what this looks like, I have no idea. It's a tangled mess, essentially. Like a yarn ball or something. So essentially what magnetic fields do, they help the gas resist collapse, but they also, well, I guess, mess things up greatly. Of course, there are other processes to make star formation even more complicated. There is something called outflows. So when gas collapses, angular momentum is conserved, which means that it's not going to just collapse to a single point. Actually, what it's going to do, it's going to form a disk. So around the collapse center, you will form a disk. And through this disk, this protostar, this young star, will be just, accreting, eating gas. However, it also does something peculiar. From time to time, it's going to expel a large amount of gas with large velocity perpendicular to that plane. And this will actually greatly affect the surrounding of this young star. So I'm going to show you a simulation about this. This is a bit tricky to understand this one. So in this one, the color means temperature, essentially. And what you are going to see is that as the gas cloud collapses, you form your central protostar, your seed star, essentially. But soon after that, it will start emitting these high temperature, high velocity outflows. And if you just wait a moment more, you will start seeing the final picture, which is that you have your central star, you have these bipolar outflows coming out of it. And if you have good eyes, you can also see the disk also still forming around it. So, all right, young stars have some outflows and disrupt their environment, but stars do one more thing that we all know. Stars shine. We have a lot of experience with that from our very own star, from the sun. And when stars shine, they heat up their surrounding and they exert pressure too on their surrounding. So in this simulation, you can see that this young star here is essentially heating up and pushing away the gas around it, essentially blowing bubbles in the gas, which makes it harder for gas to fall onto it. So it's, in some sense, regulating its own feeding. So that's what one star does. So imagine if you have a cloud that forms a lot of stars. What happens then? In that case, what happens is that each of them blows bubbles around it, and soon the combined effect of all these stars will essentially just blow away the rest of the gas. And you will see that soon in that simulation as more and more stars form. These white particles are the stars. All the gas gets blown out. So this is actually the reason why that this is actually the reason why that there is still gas left in our galaxy or any galaxy. Why, not all of the gas gets turned into stars. And of course, there is one more complication with star formation, which is the fact that massive stars, big stars, they die young. They are very, very bright, but they die young. And when they die, they explode in what's called a supernova. So this explosion is extremely powerful. It will obliterate whatever is left of the cloud, but even more, it's going to affect the surrounding, the entire neighborhood in the galaxy. So it's actually a long-range feedback. So what this simulation is showing you here is a simulated galaxy. So this is gas, what you're seeing here, and what you should watch out for when it turns edge on. You should be able to see these explosions happening, blowing gas out and driving the turbulence and winds in the galaxy, essentially keeping the whole galaxy running. Yeah. So like there you can see. So what's the takeaway? Star formation is extremely complicated, messy, and there is this problem here that we physicists often struggle with, which is small and large scales interacting each other. So what I mean by that is that when a star explodes, for example, with a supernova, it affects a giant region, a region that's about 10 billion times larger than itself. And this makes it extremely hard to simulate or even calculate anything for this problem. However, we are trying, and there are a lot of very interesting questions in this field, but I'm going to talk about the one thing I'm interested in currently, and this is called the initial mass function of stars. So this is a fancy phrase for essentially the relative frequency of stars of different masses. So what we do is we look at how many stars are of one solar mass, two solar mass, and just make a plot to show what's the relative frequency, which one is more common, how common are small stars, large stars. And if you do that for the neighborhood of our solar system or for the Milky Way, you get a function like this. So essentially, this shows the mass of stars. This is how frequent they are. And what you find is that it's actually a very simple shape. It's essentially a straight line, and it cuts off at some high value and some low value. That's essentially all it is. So what it shows is that, what we find is that the sun is not the most common type of stars, unfortunately. Actually, the most common type of stars are a bit smaller. But what's actually really interesting is that when we construct this function at different places of the Milky Way, if we look at all stars, or we look at the stars that are forming right now, or we look at in a neighboring galaxy, or we look at regions with different densities, temperatures, pressure, what we find is that this function is always the same. For some reason, with all this complex physics, with all these different properties, you still get, for some reason, for some reason you still get that 0.3 solar mass is the most common. Why? And truth be told, I don't know the answer. I have some ideas, of course, but one way to test this, and that's what we are really looking forward to, is to look at extreme regions. So as I said, if you look at old stars in the Milky Way, young stars, or even our neighbor in galaxies, we found, oh, it's always the same. But what if you look at a place that's truly very, very different from our neighborhood? So such a place would be a massive elliptical galaxy that formed older stars really, really long time ago and now just stopped doing it completely. Or if we look at the center of the Milky Way, anyone knows what's at the center of the Milky Way that makes this place super special? Yeah. Next to a supermassive black hole that can create all kinds of tidal forces, compressed clouds, what's happening there? And we can also look at what happens in very, very small galaxies. And I know it's an ultra-faint galaxy and you can't see it with this contrast, so I guess it's appropriate. So these are places that we would really like to have a better look at. And of course, I don't want to plug JWST anymore, but that would be really useful for this as well. So I'm just going to leave my summary slide here. So the takeaway would be, to form stars, you need hydrogen, you need a bunch of really, really complicated physical processes, and you get stars. And there are all these questions that we would really like to know the answers to, and hopefully we will soon. Thank you.
All right. Very well done, David. Let's take a few questions. Let's start right here up front.
I was wondering of these different effects, the complexities of these effects. Is one of these bigger or have more influence on the spinning action against accretion disk? One of these drive that rotation more than another?
So if I understand correctly, the question is, which of these processes affects the spin of the accretion disk around the protostar? I don't think you're going to like the answer. So the answer is, I think, all except the supernovae. So essentially, turbulence, naturally, that's everywhere. You can't really get rid of it. Magnetic fields, yeah, they definitely set the alignment and they influence the spin of the disk too. Radiation can destroy the disk, but probably that's I would say one of the stronger ones. Outflows, definitely, they need them to form. Supernova, by the time these happen, they no longer have the disks. So, yeah.
All right, however, right there.
Do we know yet whether the first galaxies were formed from stars or whether they were formed from gas and then the stars formed inside those gigantic galaxies?
So if I understand correctly, the question is about the first galaxies and the first stars. So do I understand?
Yeah, so which came first, like the first gas clouds, or did the stars kind of form as a result of the Big Bang or something along those lines?
Did the galaxies form out of stars that
Okay.
were created independently?
Mm.
Or
So,
the other way around?
Do you get the
okay,
question?
so
Yeah.
okay, it's a kind of a chicken egg question, but yeah. So the answer is that so when galaxies form because dark matter there's this large blobs of dark matter that essentially attracts regular matter as well. So in that sense, I would say that's probably the progenitor there. However, as the gas is pouring in, it can fragment and form dense regions which can form stars. So these are, I would say, happening at essentially the same time. But the first stars are actually very interesting. I didn't talk about it in the sense that these processes are very different for the first stars, because for the first stars, it's really pure hydrogen. So there are no other trace elements which actually greatly influence like how radiation happens. There's a different background, so magnetic field might be not as important, and everything is going to be extremely different for those stars.
All right, we had a question in the back, and then you.
Talk about how outflows from star formations are different from quasars?
So outflows from stars.
So outflows from stars versus outflows from quasars. So if you ask the physicist in me, they are very similar mechanism. It's as you have some disk. You are taking gas out of it onto an object which expels it in around its poles. So there is a similar mechanism, but because of the different properties, it's not exactly the same. And the reason I can't give you a proper answer is because I know for a fact that we don't really know exactly what is launching outflows for protostellar disks and for protostars. For quasars, I'm not an expert, but I would wager a guess we don't know that either. So, but the physical system, you're right, is very similar, and I wouldn't be surprised if there is a very similar process in them.
All these open questions keep us with job security. All right, how about right here?
How do we measure the temperature of gas clouds? So, roughly, yes.
How do we know it's 10 Kelvin?
Oh, okay. So I'm not an observer, I'm a theorist. So just to preface that. So I'm going to list several ways of doing it, and the others can correct me which of those are feasible. So one way of doing it would be if there is nothing obstructing you there, you could just try to see, and if it's dense enough, you might just go for black body, but I don't think they are doing that. It's probably not dense enough for that. So just there's a radiation temperature for black bodies. You can try to assign that, but that's not the way to go. I think what they're doing is that they're observing spectral lines, and they always have a line width. So I would imagine, so that line width comes from having a high temperature or by having turbulent motion. So I will guess there is one more way that you can disentangle the two. But as I said, I'm not an observer. I just take it for granted what they say.
If you think back to the first talk where Rebecca showed the spectrum where they had a bunch of little wiggles atop the spectrum of radiation, those wiggles give us a lot of diagnostic information where we can tease out things like temperature. All right, maybe one more question and then we will call it up top et al. If not, we will end it right here.
How much time does it take for a star to be fully formed?
So how much time does it take for a star to form? It's a tricky question in the sense, what's your start state? What do you start on? Do you start from the giant cloud? Do you start from the core? From where?
Order of magnitude.
Oh. Yeah, it's actually not that long, like millions of years for a cloud to. It's not long compared to the life of for the sun that lives like 10 billion years. So compared to that, it's actually like change. But the reason supernovae actually matter is because these massive stars, they only live a few million years, which is comparable to the time it would take to turn all the gas in a cloud into stars. So that's why it's important that they blow up.
Yeah. And I think you had mentioned, so fun fact, we are office mates. I think you had mentioned that this is your first public level talk that you did in English,
Yes.
which is pretty impressive. So let's give a round of applause to David.